Hello, everybody. Welcome to our first meeting of winter 2022. A couple of things before we get started. Can you see me? No, you can't. We got a search and rescue exercise going on this Sunday at 1300 1 p.m. Come join us as we search for somebody. It's going to be fun. I can't go into too much detail. But you're going to enjoy it. It's coming out. Anybody is welcome. You don't need a license to help with the searching and stuff. And it's going to be fun meeting in the courtyard outside the shack. And then
Sorry, that was Saturday or Sunday, Kevin?
Saturday.
Okay.
At 1300. And then in a couple weeks, we're helping out with the March Triathlon Series on March 20th. It's in March, believe it or not. They need a couple hands to go out there and help with the radios and the talking and the coordination and stuff. So if anybody else wants to come, any other club members want to come out and help us out, please let me know. We could use a couple extra people. They're pretty short on volunteers since it is the Sunday right before spring break and a bunch of people are going home. So please let me know if you are free and able to help out. Also, I have to start submitting e-plans soon for events next quarter. So if you particularly want to do anything, anything you especially are excited to do at a particular time, really next quarter, let me know. And yeah, awesome, Jack.
Yeah, this is Jack, KK6Y. We have a quick announcement that anyone who's interested in helping out with the Pacific Coast Ranch Railroad, or I'm not sure if that's the proper acronym, but the PCR project, the train radio project, we're planning on doing this on 2 days, April 2nd and April 10th. If you're interested, we're going to be sending out a sign-up form, and we ask that if you are interested, that please make sure that if you do say that you want to come, that you are available to come on those dates, because we don't want to show up with nobody there. But you'll be rewarded with food and a lot of radio experience. It should be a lot of fun. And maybe a train ride.
Trains. What day Sunday?
Oh, and then there's a work day this Sunday. If you're interested, at 11 a.m., we're going to be working on a lot of projects. We're going to be working on a lot of ARDC grant-related projects, some shack stuff. Yeah, so come on out, and no experience is required. That's all I've got.
Awesome, man. Without further ado, I guess we shall hand it up to Marcel, who's going to talk about a bunch of cool stuff. That was a detailed introduction.
Cool. All righty, do a screen share. How's my audio check? 1, 2, 3, 5, 1, 2, 6. Excellent. And you can see the screen?
Yep.
Cool. All right. Well, hello, everyone. My name is Marcel Stieber, AI6MS. I will give my brief intro, but today we're talking about off-grid solar systems for radio sites. So specifically radio sites, and that kind of keeps the conversation focused. Got a bunch of slides to go through. Feel free to ask questions whenever. Super chill, small group. So whatever you guys would like to cover, we can go over. So for those that don't know me, we'll see, make sure these slides are actually going forward. There we go. My name is Marcel, AI6MS. I was licensed in 2008 as KI6QDJ while I was at Cal Poly, so sophomore year, I believe it was, before we were offering licensing on campus. Did my EE 4+1 BMS degree while I was there with the focus on RF and communications. Also took the solar classes, photovoltaics classes, and a couple others. Did a lot of little projects while I was at Poly too, so it's always fun. I'm currently industry advisor to the club, for those that don't know. I also do repeater trustee and help out a bunch of events with communications and repeater planning and tower climbing and that sort of stuff. I've been playing with solar since about 2010, so since I was a student, not counting 1995 before some of you were born. but when I was playing with like the little solar panels on little Legos and that sort of stuff, but that doesn't really count. So I currently have 2 off-grid radio sites deployed. One of them has been running nonstop since 2016, which is just about at 5.5 years now. So that's pretty exciting, something I'm very proud of. And hopefully that's street cred to be able to do this. So today we're going to talk about kind of budgeting. So how we design off-grid solar systems, including the power budgets, some equipment selection kind of criteria and thoughts, and then maintenance overall to kind of go through what the design process is to designing an off-grid radio site. This will apply to some of the projects that the club's currently working on and thinking about doing. So hopefully we can kind of adjust some of the slides and questions accordingly. Okay. So yeah, we're going to go through the different pieces, talk about solar systems overall, then talk about loads, talk about batteries, talk about panels, talk about controllers, and then how to put it together and do some maintenance on it and talk through those. This is a cool little picture. This is the WB6ECE site, one of their radio sites up in the Santa Cruz Mountains next to a solar water tank. They just have 2 solar panels and a little metal storage NAC box behind it. And you'll see the little microwave link and the antenna for the actual repeater. So it's a simulcast system up in the Bay Area. Pretty cool. That's the sort of thing we do. This photo is at Wildflower Triathlon at the Benchmark site a number of years ago. And again, little solar panel down below that was just running an APRS Digi while the site was up there before we brought out the all the equipment for the actual weekend. But that kind of gives you an idea of the sorts of things that you can do. So first off, why solar? The funny answer is always, well, you need to power your radios, right? So we all have our radio addiction and we need to find a way to get power to them. Grid power is expensive, right? If you're trying to run like PG&E out to your radio site, it could be pretty expensive to like have them run even just the last 100 yards to your radio site. That can be tens of thousands of dollars if they need to do, environmental assessments or put in poles or a new transformer or chop down trees. That gets challenging. So off-grid gives you that independence. And generally, there's kind of a low operating cost. Once you have it installed, we'll talk about some of the maintenance and replacement costs later. The actual operating costs are very low. So that's kind of nice, especially if it's like a one-time grant. You want to get some money to do something. Once it's deployed, it's kind of just there. That radio site that I put in 5 years ago, I've literally spent $0 on it since we deployed it, which is awesome. So it's been running nonstop, powering that site for 5.5 years. The only time and effort I've spent on it is occasionally going up and brushing some dust off the solar panels. That's the extent of the maintenance. So it kind of gives you an idea. When we talk about today's talk, I want to separate between residential and radio sites. So residential solar or like grid tied solar usually requires an inverter where you're dealing with AC loads. You're trying to power AC systems, 120 volts, microwaves, fridges, TVs, computers, that sort of thing. So in this little block diagram, you'd have this inverter and load, AC loads down in the bottom corner. You might also have a grid tie in here. So like residential solar systems at home will have a grid tie inverter. They might not even have a battery system, right? So they just have this bottom right corner and none of the rest of it. On radio sites, it's usually the other way around. If it's a smaller off-grid radio site, often you're going to try to run everything on DC. You don't have to do any conversion then. You can just run it natively off the battery voltages. So we're just going to focus today on those 4 blocks. So solar panels, solar controller, a battery bank, and then your loads. And I guess I should add a dotted line. Sometimes your loads would be hooked up directly to your battery bank. Sometimes it goes through your controller. So the assumptions for today: off-grid, no AC power, DC loads only, no inverters. And then the design is going to be trying to use off-the-shelf solutions. So kind of a system assembly versus like designing this from scratch. I'm not going to go into MPPT controller design. Don't worry, it's not an EE class. Okay, so our mental model for off-grid solar systems. Assuming that your goal is, and I should probably flip the slide around. So assuming your goal is 100% uptime, so that means that the system's always running and never down, then we need to design the system for our worst case. And our worst case means the shortest time of the year, which is over the winter solstice, right? December 21st, whatever that is. The coldest temperatures of the year, the cloudiest days of the year, and the most system load, right? So there's this worst case of worst case of worst case. So it's this very corner case that you have to design for to make sure that you have enough power to still run your system in that corner case. Again, that's if you need 100% uptime. If you don't need 100% uptime, you're okay with your system occasionally turning off for a day or a night or something, then you don't have to design for that worst case. And often that'll be a trade-off that you make. So some of the temporary sites I've deployed, I'm okay if our average battery level goes down slowly over a week time, as long as at the end of that week I still have power. And maybe I'm okay if the repeater turns off from 2 a.m. till the sun rises because we don't need it during that time, right? So then I could use a smaller battery bank, right? So there's some trade-offs you can make, but generally we're going to focus on 100% uptime, and you can always scale it back from there, right? So for the case study, we'll use that site that I've talked about several times now. This is my nonstop site that's been running for 5.5 years. So this is Cupertino Aries ArcNet project. So this is our wireless internet site. It's kind of like Arden that we're currently deploying in SLO County. And what it has is an uplink radio, an access point, a webcam, and a phone adapter, so an analog phone adapter. So you can see here on the shipping container, top right, there's that mast. There's a little SXT high gain pointed up at the sector site. A little Ubiquiti Pico station access point, and then a little webcam pointed down at the door. So pretty simple little setup. Okay, so first part is DC loads. I should ask, any questions so far? Exciting, okay. So DC loads. So when we think about what we're gonna do, we first have to figure out what we're powering, right? So is this a weather station site? Is this a repeater? Is this an APRS digipeater? Is this a mesh network node like for Arden? Is this a remote base HF station? Do you need to run like a small air conditioning or heating unit? Do you need to run fans or lights or other security systems? Like what are you actually powering? This is the signal boxes up at Radio Hill at Wildflower as well. So this was one of the temporary setups we set up. And that one had a repeater at it, which was powered by a little timer. And we went up for the weekend when we were doing work days. You could just turn the timer up to 6 or 12 hours or whatever, and it would run the repeater for that amount of time. The battery would just get charged up by the solar panel during the day. And if it ran out, before the 12 hours was up, then it did. It wasn't mission critical. So when we think about how much power we need, and I'm going to try to keep it light on the math here for you guys, right? But we're kind of do the watt hours per day, right? So watt hours per day of usage is kind of our baseline to figure out how much power we need for this system. So if we're running a 50 watt repeater at 100% duty cycle, that's when you actually look at the data sheet for like a Yaesu DR2X, it's about 150 watts of DC power, so it's pretty chunky. So 150 watts of DC power times 24 hours gets you 5,700 watt hours per day. Right, so that's a lot. That same repeater only running at 10% duty cycle, which is about 20 watts on receive, puts you down at only about 800 watt hours. Right, so you can see there's a huge difference depending on how you're calculating this. Your average repeater, like CPARC's repeater, is probably only running 5 or 10% duty cycle most of the time, if that. Right, if you think about how often is it actually transmitting during an average week, that's your duty cycle number. Now, the problem that you have to consider here is if this is an emergency system that needs to be able to respond in emergency and have enough power to run in an emergency, if you're running a net full time on that repeater for 24 hours during a power outage, that there's a flood and a tsunami and whatever else all happening at once, then you need to make sure that you have enough power to support that repeater running at potentially 100% duty cycle for some amount of time. You're probably not going to run 24 hours at 100% duty cycle, but maybe a couple hours worth of a net you may need to make sure to support. So that's really important when you think about it. And if you compare that to like a 10 watt digipeater at 100% duty cycle, that's only 240 watt hours per day, right? So dropping the power output of your system, reducing your DC load is a huge factor in how much power it requires. The nice thing is lots of online calculators to do this, and it's pretty straightforward. I meant to drop the slide deck in the chat here in case anyone wants to follow along. It's also on my QRZ page. Oh, it doesn't let me throw a file in there. All right, well, never mind then. We'll do it another time. So these online calculators are super useful. They let you just plug in the loads and they give you the calculation. So in this case, this was for the site, right? Uplink radio, access point, webcam, telephone adapter. Oh, and the Ethernet switch. Don't forget little things like that. Or sometimes a fan might be at the site, right? If your fan's running for half the day, you need to make sure that that's in your power budget as well. So add those all in, number of hours that it's on per day, right? So sometimes if you have like a light at the site, you might not turn the light on during the day, so you can save some power. You can kind of figure out how to play with those numbers. These DC watt numbers were pulled from the data sheets, right? So the data sheets for these manufacturers give you the numbers. Now, data sheets don't lie, right? Sure, Marcel. I literally just got a webcam today where the data sheet said 12 volt 1 amp. And sure enough, the bottom of the device says 12 volt 1.5 amp, and the power adapter says 12 volts 2 amps. So which is it? It's a great question. So that's that'll be one of my tests, is to put on the bench and actually measure it with different lighting loads and different IR lights on or off to actually get a real number, so you know what it takes. And that's a big lesson learned here as well. So calculating your loads, that's step one. Any questions on that? Okay, so step two is batteries. Batteries are fun. I like batteries. I have whole talks on batteries too. So if you're bored, you can hop on my YouTube channel. So historically, lead acid batteries, like deep cycle lead acid batteries, were really, those are really what you did. They just were cheap for initial deployment. They were cheap and they worked. They have the word lead in them, so they're very heavy. They aren't really a great solution for long-term sites. So the one I deployed, yep, is lead acid. Any solar site that I'm deploying these days is going to be lithium iron phosphate. The chemistry just lasts way longer, and the slight price premium you're paying initially is really worth it, right? You're not having to replace those batteries after 5 years. You can replace those batteries after 10, 20 years, depending on how often they're cycling. For this system, we're going to talk about a 12 volt system, but you could also, I'm sorry, we're actually going to talk about a 24 volt system for this one, but you could run it at a 12 volt system. You can run a 48 volt system. You can run a 36 volt system. There are a whole bunch of different voltages you could run your system at, each with their pros and cons. For a radio site, I would base it off of what the power is, what you're powering at that site, right? So for this ArcNet site, we're powering mostly 24 volt equipment. So it made sense to run it natively at 24 volts. Gives you a little bit lower current on all your cables as well, so you don't have to make your DC cables as big, but that works out nicely. What else to highlight here? Yeah, these are some old prices from, I think, 2 years ago. These prices keep dropping, so especially lithium iron phosphate. I know the club just bought one as well. They've really come down in price for some pretty big ones. I think the one you guys got is, I don't know how many amp hours, 400 amp hour, I think, and it was only 50% more expensive than the one listed on this slide. So yeah, their prices are dropping and they keep coming down, so that's pretty cool. So when we talk about battery bank sizing, again, we have to start with that daily energy usage, that watt hours per day. Then we have to apply the derating. So again, this is assuming we need 100% uptime. We have to derate how much capacity we need. So you need to plan for the number of days without sun, right? Or how many days of backup power do you need? Or if your solar panel is in a dangerous spot, or if you're relying on something else, or if you have a lot of cloudy days, you might only get 20 to 40% of your actual solar output. So if it's up in the Pacific Northwest, that could be an issue, or other cloudy areas or near the coast, for example. You have to account for that, right? You're not going to get as much solar production. If it's colder outside, pretty much all chemistries won't give you as much capacity at lower temperatures. They have a higher internal resistance as well, so the whole system's less efficient. So you have to kind of keep that in mind. Depth of discharge. So depth of discharge refers to how far you discharge that battery in that time frame. So lead acid batteries typically, you can only allow a 50% depth of discharge, and this is because they really don't like to be fully discharged. It damages them pretty badly. If you ever have drained your car battery to zero, it doesn't recover very well. It's never quite the same. Lithium iron phosphate, on the other hand, they can handle full discharge pretty well. So you can discharge those fully, so you don't have to derate them as much. So typically, if you're using a lead acid system and you kind of don't know what numbers to use, you'd use a 3-day number for 3 days of no sun or reduced sun, and at the end of those 3 days, you'd be at 50% depth of discharge. So if we plug this into some numbers, sorry math, right? So 894 watt hours per day, that was our target number. With 3 days of backup power, temperature rating for getting down to just about freezing, which for slow would probably be accurate. You know, occasionally you get some frost. And then a 50% depth of discharge, you plug in the numbers and you get a watt hour number. So watt hour of 7,510 watt hours. Now, depending on the battery voltage of the system, you divide by the nominal voltage of the system, and then you get your actual amp hour capacity. So in this case, 24 volt system would give us like 300 amp hours of lead acid. If you plug that into some online calculators, again, they can all do this for you as well. Hey, that one gave us 360 amp hours. So yeah, same ballpark order of magnitude. That's kind of what you're looking for these sorts of sites. So what does this actually look like? So this little site that we were putting together, this little ARCANET site, would require 4 200 amp hour batteries or 8 100 amp hour batteries. I think the club has a couple of those 100 amp hour batteries sitting there. Imagine 8 of those running this site, right? That's a lot of batteries for 2 little radios and a camera, right, and a phone. So it's kind of crazy. But if you actually need it to run for that long and those numbers don't lie, then that would be accurate. The thing that I found is those numbers were not accurate, right? So when I actually hooked up this whole system and ran it, even at night when all the IR LEDs are on, keep that in mind. Those are usually not running during the day. Then we got only about 18 watts of DC power, like when everything was running. So that's with a device connected to the Wi-Fi, that's with the uplink running, streaming the camera and the IR lights on, about 18 watts. So much lower than the 37 watts than we had budgeted for, right? So if we actually plug those numbers back in, we can reduce our watt hours per day about in half. So we're down to 450. We're going to reduce the number of days that we need in our system. And then when we plug that in, we get about 113 amp hours. So about a third of the capacity requirement, right? Which is 1/3 the number of batteries. So that's a pretty big deal. So what does that actually look like? Well, I took that 113 and rounded down because that's cheaper, and did 200 amp hour 12 volt batteries in series, which gets us 100 amp hours at 24 volts, right? So that's what it looks like. 2 little lead acid batteries at the bottom, the solar controller here on the middle shelf. It's the same one that the club actually has. You have those in the shed with the little controller screen. And then yes, the bricks are there because they fit nicely and prevent the batteries from sliding around in an earthquake. Someone always asks about that. But this whole thing's just a little plastic cabinet from Lowe's and just does the job. So that's high level overview of batteries. Any questions so far on this? Okay, let's talk solar panels.
I have a question.
Oh yeah, go ahead.
In that last slide that you showed us, is there any reason why the little box is facing back like that? It's lying on its back.
The little screen here in the middle, you mean? You're asking about this black screen in the middle?
Yep.
Yeah, no particular reason. It was easier to mount, I think is probably the answer. Yeah, this sits in a closed container. So these cabinet doors are normally closed and locked in the back of a shipping container. It's not a system that you're regularly like accessing or looking at or logging into. So it's really when you open up the cabinet doors, you're standing above it and looking down, and then you'd be seeing that screen. So that was just kind of a design choice for that particular installation. Yeah, if I were to install one of these and like have it residential, that screen would be set up somewhere where I could see it and interact with it and read it. These also run, a lot of these controllers run CAN bus. So this one runs RS485 and you can hook it up to a computer and add monitoring, that sort of stuff as well. I think the one the club has now is also does that. So that's pretty cool. Any other questions on batteries and stuff? Okay, solar panels. These are solar panels. You will notice the particular solar panels in this photo do not have aluminum frames on them. Pro tip, never buy solar panels that don't have aluminum frames on them. These will break very easily. It's effectively 2 large sheets of glass with cadmium telluride between them. These are weird chemistry, and they break very easily. So I would not recommend ever buying solar panels that don't have good frames on them. It's important that they are robust and can move, especially for off-grid sites. These have since been replaced, but that's another story. Okay, so solar panel mental model. So again, I'm going to briefly go back to grid tied. So for grid tied solar systems, so this is like your residential solar systems, where you're getting money for power that you give back to the power company, like back to PG&E. Your goal is to maximize annual production, right? So you want to maximize the total amount of power you're going to provide throughout a year to get the most bang for your buck, because you're installing those primarily for financial reasons. For an off-grid system, that's completely the wrong mental model. You actually want to maximize your power again for the shortest day of the year, right? In the northern hemisphere, that means you want to be pointed due south and match the angle of the sun in the winter. And this is super weird because during the summer, your solar panel will be at up some pretty steep angle. And during the summer, the sun's coming up at a really weird vertical angle down onto it. and it's really inefficient, right? You want to be perpendicular to the solar panel to get the most efficiency. But in the middle of the summer, you're gonna have tons of power at an off-grid site. By like an hour after the sun rises, your battery is gonna be full. Like quite literally, that's how some of these sites are running. When I look at their logs, it's like they drip down at night with the battery, and then first thing in the morning, the sun pops up, they charge up, and they charge up full in an hour or two. Definitely by lunchtime, they're completely full. Now in the winter, the sun is super low in the horizon. It's a shorter day, right? So you need to make sure that you're accounting for all of that. And by keeping the solar panel perpendicular to the sun at that lowest point in the sky at the shortest day of the year, you're going to get the most power out of what little sunlight is making it to your panels. So that's really key. So when we actually look at the sizing for the solar panels, the kind of two things that you need to account for in here. So one of them is the total watt hours per day. So how much power do you need? And that's kind of an average power number. And then there's a how much sun. So we use this term called peak sunlight hours, and this tells you how much sun is available there. So peak sunlight hours is defined when the sunlight is greater than 1,000 watts per square meter. And that's a very specific number. That's kind of what they use for solar panel calculations. What that means is that 7 hours of daylight, so even though it's light out, might only be 3 to 4 peak sun hours, right? So the actual like time of the year that you have these peak hours gets pretty reduced. So if you look at an insolation map, not an insulation map, sol for sun, I presume, they create maps for the average peak sun hours for the shortest day of the year. So again, that winter solstice, the darkest time of the year, and they're sitting down how many peak sun hours you have. So in a space like San Francisco, which is kind of the closer one to the slow, 3.4 hours. In New York, it's only 2.8 hours. If you go up to Washington, it drops down to 1.4 hours. You go down to Tucson, closer to the equator, it's up to 5 hours. If you go all the way up to Alaska, it's only 0.3 hours, so a third of an hour of peak sunlight per day. So you can imagine if you look at off-grid solar sites in Canada or in Alaska, you're going to see much, much, much larger solar panels for the equivalent radio site, because they need to be able to survive on those coldest days and shortest days of the year. So if we look at our site, we're going to use that 3.4 hours of peak sunlight from San Francisco. That was near the Bay Area where this one was installed. 450 watt hours per day, that was the updated number, which gets us out to about 132 watts per day, right? So it's a pretty simple calculation to see how much solar panel sizing you want. And generally go more. There's like solar panels are cheap enough, and these prices are old. These are like $1 a watt. You can get down to 50 cents a watt or 25 cents a watt. You can buy used panels, actually quite a few sources online that resell used panels that are maybe only 5 or 10 years old. So they still have another 10, 15, 20 years of life in them of reduced capacity, but you can get them dirt cheap, right? You can get a panel that's, a 200 watt panel for 50 bucks type of thing, which is pretty awesome. I would definitely size it higher. For this particular size site, 200 watt panels, or in this case, we did one 200 watt solar panel. It was just easy. It was nice and simple to deploy. It was on sale, Amazon Prime shipping. It came in 2 days, this huge box. It was pretty amazing. It's a similar size to the panels you guys have too, so it's kind of neat. So we got, 250 watt panel in this case. So a couple key things, and this is foreshadowing to the last section. So the actual panels, so in this case with 250 watts, two key factors that you need from your panel. One is the VOC, or open circuit voltage, and the other is the short circuit current, or ISC. So that's when you look at a solar panel, when there's no load connected to it and it's under its max sunlight conditions, that'll be the maximum voltage that that panel produces. So in this case, 37 volts. And in that same condition, if you short circuit, so if you hook those leads up to an ammeter directly with no load in it, you'd get almost 9 amps of short circuit current. So that gives you kind of the power profile of that solar panel at the two extremes, and you need that for your controller sizing. Any questions on solar panels before we jump into controllers? Okay, so solar controllers, 2 types: pulse width modulated, which is not really used very often for off-grid sites. They are small and cheap. Your Harbor Freight Special is one of these, but they're lower efficiency. You have to have tighter matching between your solar panels and your batteries, and they're generally not a good idea. not for radio sites. They're noisier because PWM pulse width modulated means different times of day and different sunlight hours will give you different RF noise. So it's really hard and annoying to debug issues. There was an issue with an off-grid radio site that had a bad controller. And it turns out that every morning between like 9 and noon, when it was charging up the batteries, they had some really weird interference and intermod problems. So that was solved by buying a nicer controller. So my recommendation, buy a nicer controller from the beginning. So MPPT controllers are the nicer controller, maximum power point tracking. These are highly efficient, very compatible. Most of them can buck and boost depending on the type of controller that they can handle higher or lower voltages than your solar panel. So a lot of options for how they operate. A lot of cool stats on these. Again, some of these have Wi-Fi and Bluetooth connections. Some of them have serial connections or other things. This is mine. One of mine, this is a EPever Triron, and this one has USB ports on it and the RS-485, and you can hook up Bluetooth to it, and yeah, they're quite nice. So this is one of the bigger ones, but they also make smaller ones, and that does a lot. So I use that to run my home office setup when we had a power outage for a whole day. I ran that with the battery and a solar panel, and happily ran my computer and monitors all day long, which was good fun, great experience. Okay, when we're talking about solar controllers, a couple things you need to figure out for sizing, right? So one is the total solar panel wattage. So how many watts of solar panels are you dealing with? What battery voltages are you dealing with? And then what are your peak load currents? And then we talked about this earlier, but the maximum input voltage, and this was Jack's question at the very beginning too, the maximum input voltage for that controller is critical, right? So if we do a little case study here for this 250 watt panel that we had, we're running a 24 volt battery system and we had about a 2 amp load. This is what we like. These are two different models we could look at. So these two models, they both had 12 or 24 volt auto recognition for system voltage. Great, so they're compatible with this. The rated battery current was fine to 20 amps versus 40 amps, and you can usually set that lower if it's a programmable one. The load current was key for us. We had to be at least 2 amps. This site is well under that, so it doesn't really matter. The input solar voltage, solar short circuit current had to be less than 25 amps. We're only at about 9 amps, so that's great. The battery voltage range 8 to 32, we're good. The maximum solar input voltage 150 volts DC, we're at 37. That's good, right? So again, this controller 150 volts DC could take those big solar panels out in the courtyard. Those are 76 volts open circuit, something like that. They're very high at this abnormal kind of height, so you have to make sure you get the right type of controller for them. The other thing here to point out is this maximum solar input power. So what you'll notice here is depending on the battery voltage of your system, you can't handle as much solar power. And the reason for that is just current, right? So their input circuitry has a current limit here, which you can calculate by doing the division there. And if you have a higher battery voltage, then for the same current, you can take more solar panels. So that's kind of cool. So if you want a really big solar panel system, bumping up the voltage of your system will help a lot. Because then the battery voltage of your system, I should say, then you can deal with a smaller controller, fewer losses. Cool. That's a basic overview of solar controllers. Any question about those? And again, this is not DC or grid tied ones. The grid tied ones are a whole nother talk on that.
I had a quick question.
Yeah.
What was the model of that controller you just held up a moment ago, please?
The model of the controller I just held up is the Triron 2210N, November. Tango Romeo India Romeo Oscar November 2210 November. That's a pretty nice one. So I picked that one up specifically because I'm trying to remember exactly. I thought this one had Bluetooth built in. I think it doesn't. It has like the interface control that I can. This one I don't think has Bluetooth in it, but I have the USB cable that goes to the RS-485 port, so you can plug that into the front, and then you can actually USB OTG this to your phone. I think that's what I did last time. Or you can do that to your computer, and you can program it to your computer. I have it hooked up to a Raspberry Pi to do monitoring and get the stats from it. Because that's really nice. Is being able to get the stats from the system is pretty fun.
The Bluetooth is for going to your phone?
Yeah, this one doesn't have Bluetooth. Some of the a lot of the Victrons have Bluetooth, and I think EPever has a couple others that have Bluetooth built in. So that's kind of nice. really handy if you're setting up temporary sites, you can just set it up and deploy it. For off-grid sites, especially if they're remote off-grid sites, having that telemetry is really, really nice. So the site that I'm currently talking about, I actually don't have good remote telemetry for it, so I don't have a good way to like track it over time. I should throw a Raspberry Pi there and plug it into the RS485 port and start logging that data. That'd be really nice to have. So that's definitely something to consider. Is I wish I had that on some of my sites. Okay, take 15 seconds, look at this image and tell me what's wrong with it, or what do you observe? Something about the solar panels.
They look quite dusty.
They look dusty. Okay, it's a reflection of the sky,
Okay.
but they do look
Discolored.
discolored. Very good. So if you notice the different colors here, this first one's kind of like bluish, the next one's red, and then it's kind of green, then blue, then red, then blue again. I don't know. Maybe tweak your eyes a little bit. They're all very different. These are your Harbor Freight special. So these are thin film panels. It's a printing process that they use to make these. And when you get cheap panels, you'll have lower quality control and wider process margins. So these panels are not well matched to each other, which might be okay. For the price point, yeah, they're not bad. I've run a number of sites with these off grid and it works, but they're nowhere near as efficient or as high quality as getting better panels or name brand panels. So just something to keep in mind. I loved that because this was up at Wildflower again. We set up a temporary setup with 6 of these panels to run that repeater that I showed you earlier. And it worked, but it wasn't ideal. Okay, so deployment. So this is the actual site, the ArcNet site that we did. You'll notice the left side here, solar panel, solar controller, and battery bank. It's pretty straightforward. Jack will notice that I love doing drawings like this. It's very helpful to just draw what you're doing and document it, right? This was as deployed in 2016. So I had my initial drawing, and then once I actually deployed it, I made a couple edits, and then that's the final drawing. That's exactly what's up there. So I remember how we wired it, where it's going, and everything. In this case, we had 24-volt PoE, passive PoE injectors for the 2 passive PoE devices. We had 1 active PoE injector for the webcam because it required 802.3 AF. And then we had to have 1 24 down to 12-volt converter to power the Ethernet switch and the analog telephone adapter. Kind of annoying, but hey, you make it work. I chose that route, right? The other way I could have done it is made this a 12-volt system and then boosted up to these other, to the PoE injectors. This was the more efficient way to do it because these radios came with their injectors, so those were already free. And then a conversion down, that's a pretty low current as well because the Ethernet switch and the ATA barely take any current, so that's pretty easy to do. These days, if I were to do this again, I would probably use Ubiquiti's SunMax solar controller because for these types of devices, not the webcam I'd need a dedicated injector for, but the 24-volt PoE you can get natively from there, and none of this is running more than 100 megabits. So that would work totally fine. Yeah, so that's that one. When you put that onto paper, this is what, or take it off the paper and put it onto plastic, this is what it looks like. So there's just one of those plastic shelves from that cabinet that I showed you. And everything's zip tied down, everything's labeled, all the voltages are labeled. Because keep in mind, we've got 3 different voltage domains in this. We've got 12 volts, 24 volts, and 48 volts for the active PoE. And this one's actually, I realized that that other drawing doesn't have the 24 to 48 volt converter, which is here on the top right. So that's actually powering the active PoE injector. So this sort of setup, what's one other thing you notice that's missing on here? There's a certain type of connector that you don't see on here that's very common for amateur radio. A little black and red connector. Do you guys have a crimper for? Kevin knows the answer. Helen knows the answer. Anderson power pole.
Say it louder.
Powerful.
Power pole. There we go. Yeah, you weren't saying it loud enough. Yeah, so no power poles on here. Why are there no power poles on here, Marcel? This is a ham system. Well, Marcel, there are a whole bunch of voltages in here that would kill your radio if you plug them in, right? So I'm definitely not using a standard power pole on anything here except for maybe the 12 volt. But realistically, this system isn't designed to have someone go up and plug into it. right? So I don't want to make it compatible with the standard because I don't want the standard to interface with this. The system is designed to run 24-volt equipment off grid, and its power budget is designed for this. Now, if a ham in an emergency gets into this cabinet and pulls out one of the batteries that's fully charged and plugs their radio directly onto the battery, great, that'll work, right? They can just plug into the 12 volts. Other than that, I very intentionally made that design decision to exclude Anderson power poles from the setup. So keep that in mind too when you're building something. For the actual solar connections, we use MC4 connectors. That's the kind of solar standard these days. But yeah, so here's that cabinet again. You'll see the equipment shelf on the top, solar controller in the middle, batteries in the bottom. And then this is that solar panel on the roof. Just built a simple frame out of some aluminum square tubing from Home Depot, bolted it to the roof with some nice silicone goop to prevent any leakage. And it's got a very steep angle. We didn't do this one very accurately. It could have been steeper. This was kind of a trade-off for wind loading versus bird pooping versus dust getting on the thing versus being steep enough to give us the most power in the shortest day of the year, right? So there's always kind of trade-offs there. You'll notice the solar panel just in front of it here on the ground. These roof vents are solar panels and they've got a bunch of dirt on them as well. Those do get washed off a little bit in the sunlight or in the rain and stuff, but they also, because they're horizontal, they collect quite a bit of dust. So that's one thing to keep in mind when you're installing them. But yeah, that panel looks very clean when you first install it. Remember this photo. Okay, last section, maintenance. This is fun. So this is a real photo taken at Burning Man in the middle of a dust storm. That is a young lady with a leaf blower with a power cord going to an inverter on a golf cart. No joke. And she is blowing the dust off the solar panels because they get so much dust on them. So that's a relatively large array there. That's tens of kilowatt hours. Pretty big system, but that's something you have to keep in mind that there are maintenance considerations. So the first one is batteries, right? So we talked about this a little bit at the beginning. Lead acid batteries typically only have a 5-year lifetime. So that means from the date of manufacturing, they're good for 5 years per the data sheets. That's pretty typical. Can you get longer than that? Yes. Can you get longer than that? Yes. Can it be shorter than that? Yes, as well, but then you can warranty it, right? So step one is really think about, check the data sheets and what you're buying, check the date codes on packs. If you're buying lead acid batteries, check the date code. If you go to Home Depot and pull a lead acid, they sell the little 7 amp hour ones for electric fence gate openers and that sort of thing. I found one there that was like 3 years old already sitting on the shelf from the date of manufacturer. So they should give me a 60% discount on it because it's already that old, right? So definitely check that. It's dependent on cycling, so how many times the battery cycles and how deep it's cycled, and it's dependent on the temperature. So really high temperatures will cause problem, and really low temperatures can cause problems. This is the most expensive part of maintenance for sites. So replacing batteries every 5 years gets expensive, right? So even if your initial battery cost, if you went with like a lithium iron phosphate, but it lasts for 4 times as long, even if it's 3 times as expensive, you still came out net positive if you're designing a site to run for 20 years. Now that might not be your goal. This picture here, I like, this was at my work in the parking garage. They have these batteries run the fire alarms and the lights, the emergency lights in the parking garage. And I saw them there one day with a big flatbed truck swapping out these batteries. And I got to look inside before they took it apart. What do you notice is wrong with that picture? The 4th battery from the top left is missing a lid, and the lid is down here on the lower shelf. So this particular battery pack system, so each of these cells is 1 nominal cell. So this was, I can't do that math quickly. That looks like 10 in a row. So there's like 20 cells and maybe another 10 down below that. So 30 cells in series, something along those lines. And one of them had gone poof, right? And that kills the whole string in this case because it's a big series connection. So they had to come and replace the whole packs. This building was less than 5 years old at this point. So those batteries did not last 5 years. And that was expensive to replace. That's a lot of cells to replace. So panel cleaning, I touched on it briefly. It's easy to forget about this, especially because you kind of need to check on them during the year. That beautiful shiny panel we installed within 2 months had that much dust on it. Sure, they were doing construction nearby, but that's kind of important to keep in mind. So in this case, one more reason to oversize your solar panel, right? We only needed 100 watts of this solar panel or 150 watts or something. So This is a 250 watt panel. So even if we're losing like 30 or 40% efficiency from this dust, it's still going to be fine for our application, right? So that's another thing to consider when you're buying systems or building a system. More extreme cases of dust, again, up there, that's that same woman cleaning off those solar panels, this time with a brush in the middle of the day, not in the middle of a dust storm, but same sort of mess. You can see how challenging that is. The bottom left panel here, I believe this is cement dust on one of the solar panels, and that's scraping it off, so that can be even more difficult. But again, you can kind of see the efficiency of the uncovered cells versus the covered cells. You're probably losing 50% of your efficiency there. And the one on the right here, snow on your panels can obviously be a problem. A little bit of snow is often dealt with by the panels themselves because they're dark and they absorb the sun and heat up a little bit, and they'll melt off a little bit of snow on them. But a lot of snow on them just insulates, and the snow reflects the sunlight as well. So that can be a challenge. So some systems need cleaners on them. Some need a heater that you need a little bit of extra battery power first thing in the morning to melt any snow off of the panels. And then you'll start getting actual sunlight to recharge your batteries. So those are a little bit more extreme cases, but something to keep in mind. Fortunately, in most of or good parts of California, it's a little bit more mild and you don't have to worry about those. Cool. So that's about what I had for my presentation. Open to any questions you guys have or particular ones. I've got a couple extra slides too if you want some pictures of another off-grid site. Whatever you like. Thanks, Kevin. I hear the roaring round of applause.
Yeah, very, very intense. Yeah, sure, let's see it.
Cool. So I've got, this is another one. So this was an adventure race. This was actually for one of, for my senior project, or not senior project, 420 class, I think it was, the solar class. We actually set up a temporary repeater for the Mudmash X up at Santa Margarita Lake. Here is the beautiful high security battery cover. So this is a nice Rubbermaid flipped upside down with some manzanita brush leaf branches on it. The GR1225 repeater sitting next to it. And then a little lunchbox with an APRS beacon in it. So this is how I was remotely monitoring the battery voltage at the site. This one just used the crappy solar panels from Harbor Freight and their little PWM controller, but it worked. We had the military mast set up here with 2 sets of guy lines, a little VHF dipole at the top. You can see the flag here on the little wooden frame. That's the actual orienteering flag. This was one of the checkpoints for the adventure race. So it's kind of cool. And yeah, I think that's that one. Just kind of neat. This is kind of similar to the setup that MTS did one year as well. Not as big of a tower and no solar panels. They did generator, but since you guys have been talking about that sort of thing, this sort of setup works great, right? The really cool thing about this, it's really flexible. So I did a very similar one this past summer for another adventure race over in the Eastern Sierra. We set up a repeater up on a mountaintop with a little 160 watt solar panel and a battery pack, and it just ran. It ran for a week. We set it up on midweek and then had it running through the 36-hour event through the middle of the night. No problems, never shut down, never ran out of power. Did the right power budgeting, put the stuff in the right spot, picked the right size battery, and life was good. So it's really neat the flexibility that this gives you, right? There's no generator involved. You don't have like hazards of gas and sparks everywhere. So as long as you set it up safely and put it into waterproof containers, assuming there's weather, then this works really well. Cool.
Awesome. Any questions? Comments, concerns?
Would you recommend taking the solar classes here at Cal Poly?
Yeah. So the question was, would I recommend taking the solar classes at Poly? I think so. I definitely learned quite a bit from that class. It's really good to get kind of the mental models around the calculation. So kind of a lot of what I gave you here today is kind of a preview to what that class will do as well. They'll go into a little bit more detail of how you actually calculate some of those. When you're installing systems, like talking about shading and like where the shade during which parts of the day covers how many of your panels. A lot of projects in that space, kind of learning about different voltages for panels and how those set up, and then the economics around some more larger scale systems. The really cool thing is you guys have the solar panel on campus now too, or the solar farm, I should say, up on the north end of campus. You can get a tour there too, so consider doing that maybe with the club, or tagging on to one of the other groups that does a tour up there. Lots of opportunities there to kind of see that stuff up close, especially because you have it there and it's designed to be available for students to do research on. That's a great opportunity. So I would definitely say yes. If you're interested in solar and it's something you're passionate about, it's a good way to get a 400 or 500 level class credit as well.
Do you know who we should reach out to if we're interested in that?
It's a good
Yeah.
question. There's probably a spot on the website. I'm guessing Professor Dolan would have an answer as well, because he historically has taught that solar class. I think he's teaching it as well right now. So
Do you know what the prereqs are like for that class?
I don't. My data would be 10 years old, so I'd recommend checking the catalog. Yeah, I'll keep in mind for a lot of those classes, you can get prereqs waived as well. So on paper, it might say that, but if you're passionate about it or you have some background, I definitely encourage you to speak to the professors because they want passionate people taking their classes, especially the more niche kind of 400 or 500 level tech electives. If you're interested in it, they're almost always going to want to take you into that course. So I would strongly recommend reaching out. There were some IME classes that I really regret not taking when I was at Cal Poly around electronics manufacturing and that sort of stuff, which is a lot of what I do my day job now. They offered it like once every other year for 1 quarter in one class, one section of like 6 to 10 people type of thing. If I had expressed interest a little bit earlier, they would have set up a schedule or I would have been able to take it, and they would have waived the prereqs for it. So definitely reach out. And if there are classes you're interested in, you're passionate about that topic, definitely contact the professor of the department to see about it.
Yeah, I know there's a lot of like higher level EE classes that I want to take, but there's a huge prereq chain to get to them, which I will not be able to take. So,
Yeah, EE and Aero, a couple, departments have pretty notoriously long chains. But yeah, like I said, you can break into a lot of those too, depending on what the material is. Like for the solar class, at least when I took it, there was definitely math involved, but like the EE background that you needed wasn't incredibly important or incredibly high. So I would definitely take a look at it, and see if that's something that would work for your curriculum. And you can often spin like some of those courses too, if they have like a project aspect to it, you can often spin that project towards your degree as well, right? So like for this solar one, for example, where I did that project in that class, I did it as event support for an event I was helping out volunteering with. I ran this solar project with Abesh, who was my lab partner at the time, and we did this project together. We deployed it on a weekend and then got the data from it, plotted it out, put it in our project report, and had that in for the class. It was kind of a neat way to kill 2 birds with 1 stone, and put that project together. If you want to do something, not as hands-on, or maybe do something more on the coding or data analytics side, there's definitely a lot you can do there as well with, gathering data from one of these remote sites and doing predictive analysis on it for weather input and that sort of stuff. Like that's what the Ubiquity SunPoint does. That's what a lot of solar systems do. Tesla Powerwalls do that as well, right? They'll predictively look at the weather, and if they know there's a risk of a storm, they'll generally keep their state of charge higher on their battery. If they know there's going to be less sunlight, like more clouds in the coming weeks, then they'll generally keep the state of charge higher. They won't run the batteries as low. So there's a lot of kind of AI, if you will, or predictive kind of behavior that they can program into these too. So that's like very computer science heavy in that aspect. Other questions? Cool. Well,
Awesome.
just as a reminder, I encourage you guys to play with this stuff. The club has solar panels and controllers and batteries. So if you're interested in this stuff, by all means, play with it safely. If you have questions, feel free to reach out to me over the Discord, or any of the other students. A lot of folks there have played with solar as well. Davide and Jack are all playing with it as well. So definitely play with it, have fun, and I'll see you guys around.
Awesome. Yeah, if you're watching this from home, thank you very much. Feel free to, I think Marcel had his email on there if you have any questions, or I'm pretty sure he's pretty much always on Discord as well if you're there. And then if you have any questions for us, w6bsn.org CalPolyMediaClub@gmail.com. If you're watching this on week 9, we have search and rescue going on Saturday, projects on Sunday, March Triathlon Series on March 20th, and a bunch of more stuff coming next quarter. So please reach out, and yeah, thank you very much.
Thank you. Enjoy your pizza.